This was a structure pop quiz. Question 1, figure 3.1. Describe the sequence of a reaction that can be used to produce a food additive compound Y from CH3 CH2Cl. So step 1 is there, it is converted into a nitrile group. When CN is attached, we call a nitrile group. Then a nitrile group is converted into carboxylic. We call hydrolysis is there when we use water as a reactant. The first reaction is a substitution reaction. The second is a hydrolysis. State the reagent and the condition for step 1. So step 1, when we want to replace this chlorine by a nitrile group like CN group, cyanide group. So what reagent we need? We need KCN, potassium cyanide. Because when potassium cyanide react, it will be a substitution reaction. We'll have CH3, CH2Cl reacted with KCN, potassium cyanide. So as a result, the CN will take position of chlorine and a chlorine will take position of the CN. So the reagent, what we need potassium cyanide. Even acceptable if you say a mixture of a potassium cyanide and hydrogen cyanide. And what are the conditions for this substitution reaction? The condition we use alcohol as a medium. So potassium cyanide in ethanol, and we should provide heat energy. And then we provide a heat energy. Well, this is the step 1. Give a systematic name of X. So what is a systematic name of X? There are 3 carbon. So for a 3 carbon, I should say it is prop. Between the 3 carbon atom, they will have a single bond according to this structure, because the structure will be CH3, CH2, C triple bonded with N. So between the carbon atom, there's a single bond, so it will be N. And due to this group, CN group, what we call them as nitrile. So this is propane nitrile. Prop because of 3 carbon, and ane we write full because the functional group is not starting with a wall. So we say propane, and then nitrile is there, so we write nitrile. So this is propane nitrile. Whenever we break down a substance by the action of a water, we call this as a hydrolysis. So stage 2, identify the type of a reaction that occurs when a dilute hydrochloric acid is added to X in step 2. So in this step 2, the nitrile group, whenever CN group is there, it is reacted with acid, like dilute acid is there, and a water. So as a result, what will happen? O and OH will be added to this, and the compound will dissociate, or the compound will break down by the action of a water. Whenever one of the reactant is water, what we call that as a hydrolysis. So hydrolysis of the nitrile, acid hydrolysis or the base hydrolysis of the nitrile group or the CN group will always result in a formation of carboxylic acid. That's why this has turned into a carboxylic acid. And the last one is when we are reacting a carboxylic acid with a metal, when a metal react with an acid, it will give salt and hydrogen. So this calcium will displace this hydrogen. As a result, the product will be CH3, CH2, COO in a bracket 2. Why bracket? Because the calcium has a valency 2 plus hydrogen gas will be the product. Because when acid react with a metal, the product is salt and hydrogen. So remember, whenever a nitrile group, the CN group, form a carboxylic acid, we call that as hydrolysis. And hydrolysis can be acid hydrolysis or the base hydrolysis. So identify the type of a reaction that occur when a dilute acid is added to X in step 2. So we call that as a hydrolysis. In step 3, Y and a gas are produced. Construct the equation. So because we were having a propanoic acid, CH3, CH2, COOH, and it was reacting with a metal like calcium is there. So calcium will displace this hydrogen. As a result, it will form CH3, CH2COO, in a bracket 2Ca plus H2O. Then we balance the equation by putting 2 here. So this whole equation is balanced. Acids are aqueous. The calcium was a solid. This is a salt, aqueous, and a hydrogen is a gas. These are the state symbols of these reagents. But state symbols is not having any marks here as they did not mention or specify. So if you just write the reactant and the product, that's also fine. In part B, the propanoic acid can also be formed from propane 1-ol and potassium dichromate. So the oxidation of the primary alcohol, a complete oxidation of a primary alcohol leads to a formation of a carboxylic acid. If it was a secondary alcohol, it will produce a ketone. But primary alcohol, first it will be oxidized to an aldehyde and then aldehyde will be oxidized to a carboxylic acid. So state the condition required because we want a complete oxidation. So if we want a complete oxidation, so we should heat under reflux. Use acid. No, this won't turn into a ketone. This is a primary alcohol. As you can see, propane 1-ol. So propane 1-ol is CH3, CH2, COH is there, and then CH2 you can say. So this is a primary alcohol. How it's a primary alcohol? The carbon is attached to a OH. The carbon which is attached to a OH is having one carbon chain. So whenever primary alcohols are oxidized, first they will turn into aldehyde. If we do a partial oxidation and a complete oxidation result in a formation of a carboxylic acid. But if it was a secondary, if it was propane 2-ol, so if it was a propane 2-ol and we do oxidation of a propane 2-ol, the complete oxidation of a propane 2-ol result in a formation of a ketone directly. So and we want a complete oxidation of a primary alcohol. So the complete oxidation of a primary alcohol leads to a carboxylic acid. So for oxidation, because we use acidified potassium dichromate, so what are the state conditions we need? We should first heat under reflux in acidic condition. To use acidic condition, use acid and heat under reflux for a complete oxidation. But if let's say we want to produce an aldehyde, then we don't have to use a reflux condenser. What is the difference in a reflux condenser? So when we place the condenser vertically, we call that as a reflux condenser. When during a reaction, a condenser is there, which is main purpose to remove the heat energy is placed vertically. It's a reflux condenser. The next, complete the table 3.1 to shows the number of the sigma and the pi bond present in a molecule X. So this is a molecule X. So if we draw the structure of a molecule X, which is a propane nitrile, prop means 3 carbon atoms are there. Whenever there is a single bond, it is always sigma. So when we count the number of the sigma bond, this is 1, 2, 3, 4, 5, 6, 7. And when there is a triple bond, one of them is sigma, two of them are pi. So how many are there? 1, 2, 3, 4, 5, 6, 7, and 8 of them we found as a sigma bond. How many pi bonds are there? So these two are the pi bonds. So number of the pi bonds, there are 2 pi bonds and 8 sigma bonds here. Describe the structural isomers, how we define the term structural isomers. When we have the compounds which are having a same molecular formula but they have different structures, we call them as a structural isomers. Same molecular formula, but different structures. The next is A and B are the structural isomers. So when we say structural isomers, they have different structures. So A and B are the structural isomers. Both are a straight chain molecule with only one functional group is present. Look, whenever you see, now describe the figure table 5.1 describe the observation when separate sample of A and B were added to different reagent. First, when we add 2,4-dinitrophenyl hydrazine, this is actually a test for the carbonyl group. Okay. Whenever there's a C double bonded with O group is there, actually it's a test for aldehyde and ketone both. If it is a positive result, if it's an orange precipitate, then definitely aldehyde and ketones, one of them is present. So when we add 2,4-dinitrophenyl hydrazine, we observe the orange precipitate. So this give an idea that this might be aldehyde or a ketone. And B also give a positive result. So B might be aldehyde or a ketone. So A and B are the classes of either aldehyde or a ketone. Then a toluene reagent, the toluene reagent or a silver mirror test, it is only positive result with the aldehyde. If a compound is aldehyde, it will give a positive result. If a compound is ketone, it will give a negative result. Or if you can say if it is a primary alcohol, also it will give a positive result. But if it is a secondary alcohol, so which turn into ketone, it will give a negative result. So silver mirror appears. So this give an idea that this compound A is an aldehyde. So first test identified that it is a carbonyl group, and the second test, the positive result of the second test indicate that the compound A is aldehyde. And this give a negative result. So this give an idea because it's a carbonyl group and it's a negative silver mirror test or toluene reagent. So this give an idea it's a ketone. The iodine and aqueous solution, this is actually a test to check if there's a methyl group next to carbonyl group, alkaline iodine, it will give a positive result. Like if there's C double bonded with O, next to C double bonded with O, if there is a methyl group, this will always be a positive test because both of them are giving this negative result. So it means that both of them are not having next to carbonyl, there is no methyl group, even in A or even in B. So the first test indicate both are carbonyl group, either aldehyde or ketone. Second test distinguish that A is actually an aldehyde where B is a ketone. Whereas the third test indicates that because alkaline iodine, it's a negative result. So this gives an idea that there is no methyl group next to carbonyl group. So when we want to draw the structure, so name the functional group present in both A and B. So which functional group is present in both A and B, like which is present in both? So what we will write, which is present in both. So we have a carbonyl group which is present in both because aldehyde and ketones both are carbonyl groups. So we can say the functional group which is present in both is carbonyl. And then the carbonyl group can be an aldehyde or it can be a ketone. The next is draw the structures of A and B in the boxes. So they did not specify what is structure. I can draw a skeletal formula. I can draw the displayed formula as they did not specify. But we have 5 carbon atoms. So I want to make an aldehyde. So if I want to make an aldehyde, so C double bonded with O and H will be there. And there are 5 carbons. So aldehyde definitely it will be at the end. So 1, 2, 3, 4, 5. And why I drew them in a straight chain? Because they mention here in the beginning that both are straight chained molecule. So this will have three hydrogens. This will have two hydrogen. This will have two hydrogen. This will also have two hydrogen. What about B? B is a ketone. And there's no methyl group next to carbonyl group. So I need five carbons. So I can draw two on the right and I can draw two on the left. This will have three hydrogen. Why I did not draw like this, that drawing, because there are five. But why I did not draw in this manner, that one on other side and remaining four, remaining three on the other. The reason why I did not draw this, because the iodine in alkaline solution was not reacting. If iodine was reacting in alkaline solution, then this should be the structure. But because it is not reacting, so this indicates that actually next to carbonyl group there is no methyl group. So this will have three hydrogens. This will have two hydrogens. This will have two hydrogen, and this will have three hydrogen. Is it clear? The structures of A and B. You can also draw the skeletal formula. You can also draw the skeletal formula of A and B, like if you want to draw an aldehyde. Because in a skeletal formula, we don't represent the, so oxygen is there bonded with carbon. So 1, 2, 3, 4, 5. And if I want to make ketone, I can draw up or down with the third carbon. And there is oxygen here. Why CO is in the middle? Why not on the third one? Because if I draw like this, CH3, CH2, the third one is a middle. But why not on the right fourth one, like C double bonded with O and CH3? Why did not draw like this? Because if I draw a ketone like this, next to ketone is a methyl group. And this, with iodine, it was giving a negative result. When alkaline iodine was added, it was giving a negative result. So it means there is no methyl group next to carbonyl group. That's why the only possibility that it could be there at the center. Even I cannot put it here because again it will have a methyl group next to carbonyl group. C is a structural isomer of A and B. C is a straight chain and has two functional groups. C shows one type of stereoisomerism, only one type of stereoisomerism. The table 5.2 describes the observation when separate sample of a C are added to different reagent. So with 2,4-dinitrophenyl hydrogen, there is no reaction. So if it does not react with the 2,4-dinitrophenyl hydrogen, what this give an indication? It gives an indication this is not a carbonyl group, neither aldehyde nor a ketone. With aqueous bromine, it changes from orange to colorless. So this gives an indication that there is a double bond present in this compound. And when alkaline iodine is there, it give a yellow PPT, a yellow precipitate appear. So it give an idea that, as I mentioned, alcohols can also give this positive result. Like if a carbon which is attached with OH, if it is having a methyl group, that will also be a positive test. So if a methyl group is there next to carbonyl, or a methyl group next to a carbon which is bonded with OH, that will, both cases it will give a positive result. But the first test indicates that this is not a carbonyl group. This test indicates there's a double bond, and the last test indicates that there is The iodine is there, which is reacting. So this give an idea that there might be, if it's not a carbonyl, so definitely OH is attached to a carbon, and that carbon there's a methyl group. Now the next is we have to draw the structure of compound C with the information given here. So it has two functional groups. What are the two functional groups? This indicates that there's a C double bonded with C. This one indicates, like, because it might be C double bonded with O and CH3, or it might be carbon bonded with OH and next to that is CH3. It will give a both positive result. But because the first test, the 2,4-dinitrophenyl hydrogen, it was a negative result, so this possibility is removed. So we are left with only this structure. And we have the molecular formula of a compound which contain, in the beginning they mentioned C5H10 and O. So we have C5, H10 and O, and we have to predict this structure, like drawing this structure. So first, this is confirmed that there will be CH3, C and OH will be there. That is one thing. Then it is also showing only one type of a stereoisomer. Like what does it means? It means only one possibilities is there. If there were two types of stereoisomer like cis and trans was there, in that case, what will happen? The double bond should be there in between. Like the heavy groups are there on one side. But this one type of stereoisomer, what this indicates that the carbon-carbon double bond is there at the end. So 1, 2, 3, 4, 5 carbon, and the double bond is here. So this will have how many hydrogens? This will have 2 hydrogens, this will have 1 hydrogen, and this will also have 2 hydrogen. And we just show, because either you show a displayed formula or this structural. So OH is there and CH3. Is it clear, this one? The structure of this compound which contain two functional group. What are the two functional group it is having? It is having OH group and it is having C double bonded with C group. Name the type of stereoisomerism shown by a molecule C. So stereoisomerism can be optical, can be geometrical. But because it is showing only one type, so it means it can, they already mentioned it is one type. So it means that because whenever we check the stereoisomerism can be optical, it can be geometrical. This compound contain a carbon-carbon double bond. As it contain a carbon-carbon double bond and we drew here the 2 hydrogen at the end, so it shows that it cannot be geometrical, because to be a geometrical isomer, there should be different groups attached to a carbon which is having a double bond. But as we drew the carbon-carbon double bond at the end, so this gives an indication that it is having no geometrical isomer. So what else it can have? It can have optical isomer. How it can have an optical isomer? As you can see, this carbon, the carbon is there at the center, which is having 4 different groups attached. This is one group, this is a second group, third, and the fourth. So if 4 different groups are attached to a carbon which is having like bonds, so this will show an optical isomer. So no geometrical isomer because a carbon-carbon double bond is there at the end. So type of stereoisomerism it will show optical isomerism. How to draw optical isomer and optical isomerism is not for edXL students. Like You will not, you will learn, but not now. In A2, you will learn in detail about optical isomers. D react in the presence of a sulfuric acid as a catalyst to form E and a water. What is compound E? What compound E looks like? C double bonded with O and C, so it looks like an ester. So name the functional group which is present in E. So which functional group is present in E? We can clearly see this is an ester is there. Identify the type of reaction that occur when D reacted to form E. So whenever esters are formed, what we call these type of reaction, because it is producing ester in water, so we call that as a condensation. Condensation means when two molecules join with each other and a small molecule is given off, we call condensation. And whenever alcohol is reacting with a carboxylic acid, this is ester plus water, so this is called condensation. What is reverse reaction is called, reverse is known as hydrolysis, because when water is used as a reactant or acid is used as a reactant or alkali is used as a reactant to break down the substance, we call hydrolysis. So the forward reaction is condensation. Draw the structure of a D. So it looks like a cyclic compound. And they mention D react in the presence of a sulfuric acid and it is forming E and a water is there as a product. So what actually happened that sometime a compound may like a molecule may react with its within itself with a change. What might happen because this whole is linked with each other. So if we break down, like if we open the structure, because there is no other reactant. So if I open this structure, if I break down from here, so what will happen? It will be O, C double bonded with O. So we break down. So after breaking down, one side we will put OH and another one will put H. So actually what happened, this compound was having two groups, two functional groups were there. One was alcohol, another one was a carboxylic acid. And the ends of the molecule reacted with each other. When end of the molecule reacted with each other, one lost its hydrogen and the other one lost its OH, and it as a result they combined with each other to form an ester. Is it clear how we predicted the structure of a molecule which reacted to form this ester? Any question or doubt in this? Next is the IR spectrum of a E is given, a percentage transmittance shown. So first thing, whenever you see a IR spectrum, you ignore the region below 1500 because below 1500 is called a fingerprint region. Every molecule is having a unique spectrum, infrared spectrum in this region. So we ignore that. So we just look after 1500. So what are the peaks we see? We see one peak here when we see one peak and this peak. So this peak correspond to, this is 1600, 1700, 1800. So there's a peak between 1700 and 1800. And this peak is there around 2900 or 3000. So we identify, this is a spectrum of E there. So use the figure 5.2 and the table 5.3 to predict the two differences in the absorption above 1500 in a spectrum of a D compared to E. So D is actually is having OH group was there in D. and there is carboxylic group as well in D. But in E, it is C double bonded with O and O is there. So if we talk about D, the compound D was having alcohol. So OH of alcohol or hydroxy is there. Whenever like this OH group is there, what is the absorption for this? A broad absorption will be there with a carbonyl OH, like carbonyl means like C double bonded with O and OH. So this OH is absorption from 2500 to 3000. And this C double bonded with O is there. When we talk about the esters, so for ester, the C double bonded with O absorption will be there 1710 to 1750. This range will be there. And for CO, for hydroxy, like alcohol, because this will have OH, they will have the same range. But we don't need, because we need above 1500. So this cannot be used to distinguish. So what are the peaks we can use to distinguish between the compound? A carboxyl D was having OH group. So in E, what we will find? We'll find ester, like this we will find in E. This will be there in E. C double bonded with O. Doesn't D have C? Yeah, D is also having C double bonded with O. So this peak, as you can see here, the order. So for a carbonyl group, when you see C double bonded, this is for ester. 70, like for ester, it is there. For E, C double bonded with 1710 to 1750. But the C double bonded with O for a carbonyl, this will be there in D. So if this peak belongs to D, the compound which is having the C double bonded with O, it will be 1670 to 1740. And then we have CO as well. But see, why we ignore CO? Because in the question, we need above 1500. So we don't bother about this part. What else we will have? Like for D, we'll have OH also. So this will be there in D because D also contain OH. And 13, 20, like this both will be there in D. We just want to work out the difference. Like these two will be there. In a compound D, the major peak will be OH, which is in the range of this. How does D is having CO? Why D is having CO? Because carbon will be bonded with OH here. So this carbon and OH, that's why D is also having this CO. But CO is not the one which we look for. We are looking for above 1500. So when we are looking for above 1500, this peak we'll get for esters, like we'll get a peak for 1710 to 1750 for E. And for D, what we'll get, because it is having OH is there for a carbonyl group, so we'll get these two peaks to 2500 to 3000 and 3200 to 3600. Because for OH alone, this will be the peak. And when the OH is there next to carbonyl group, when OH is there next to carbonyl group, so this is a peak. So these two peaks will be there in D, but one of the peak will be there in E. That we just have to mention a difference. Is it clear? How you will write the answer? You will mention that in D, It has peaks due to OH ranging from 2,500 to 3,000 due to and 3,200 to 3,600. Wherein E, it will have a peak from 17 due to C double bonded with O in a range of 1710 to 1750. That is what you're supposed to write there.